Hello everyone, welcome back. And in today's video, we are going to solve some more problems from the sample paper. We have already covered till problem 5 in the previous two videos. So now we're going to start with the next problems. So this problem is based on thermodynamics. So we have a mole of an ideal gas that undergoes a process as shown in the following PV cycle, where the path follows 5, 1, 2, 3, 4, 1. So we start from the state V2 over here, then it gets expanded and then it follows this cyclic process. Okay, so the process 1 to 2 and 3 to 4, which corresponds to these two processes. So these are given to be adiabatic, and the whole cycle is carried out using air with an adiabatic index of 1.5. So the value of gamma is given to be 1.5. Now the compression factor K, which is defined as the ratio of the largest and the smallest volume in the process, is given to be K equals 10. So if you look at the diagram, so the states 1 and 4 have the same volume, and the states 2, 3 and 5 are having the same volume. So the ratio of the larger volume is what is K, which is 10. So basically if I take the volume at state 2 to be V, at state 4 it will be 10V. Okay, now neta is the efficiency of the cycle, and T1, T2, T3, T4 denote the temperatures at point 1, 2, 3, 4 respectively. Then we have to talk about the following options. So I'm seeing a lot of temperatures. So in the options they are asking some ratio of temperatures and efficiency. So first let's talk about the efficiency. So firstly, efficiency, we have to talk about the efficiency of this cycle, which is basically 1, 2, 3, 4, 1. So now if you observe the diagram, they have mentioned that Q1 is the heat supplied to the gas to go from state 2 to state 3. So now if I apply first law of thermodynamics, observing state 2 to state 3. So as we can see, it's clearly an isochoric process, which means work done by the gas would be 0. And it's given that a heat of Q1 is supplied to the gas. So we can say Q1 equals delta U from 2 to 3, which we can also write it as NCV T3 minus T2. Now the adiabatic index gamma was given to be 1.5. So the formula for CV is R divided by gamma minus 1, where R is the ideal gas constant. Gamma minus 1 would be 0.5. So this comes out to be 2R. If we need it in case of some calculations, we'll use it. So we figured out Q1 in terms of T3 and T2. Now Q2 from the diagram is the heat rejected in the process 4 to 1. Okay, so now let's write first law of thermodynamics for the process of 4 to 1. Now it is again an isochoric process, so the work done by the gas would be 0. So the heat rejected, so Q2 would be equal to delta U, which is NCV T1 minus T4. So as you can see, it's negative. So if I take a negative sign common, this will be T4 minus T1. Okay, so now we have figured out Q2 as well. Now the value of heat transfer for the process of 1 to 2 and the process 3 to 4 are both 0 as the process is given to be adiabatic. So now if I apply the first law of thermodynamics for the complete cycle, so again Q equals del U plus W. So the net heat transfer into the system for the whole cyclic process is Q1 minus Q2, and this is equal to delta U. Now for the cyclic process, delta U is 0 plus the net work output. So from here we'll get the net work output as Q1 minus Q2. Now guys, the efficiency of a cycle is defined as the maximum work output that we can obtain for a given heat input. So in this case, the heat given to the thermodynamic system is Q1. So in the denominator there will be Q1, and in the numerator we'll write the work output that we obtain. So let's say if hypothetically there is a cycle whose efficiency is 50%, then the work output that we obtain from the cycle is half the heat supplied, and the other half will not be converted into work basically. Okay, so in this case, the work output is Q1 minus Q2, and the heat input is Q1. So as we can see, so the efficiency this comes out to be 1 minus Q2 by Q1. Now if you look at option D, it's given as 1 minus Q1 by Q2. So option D will be wrong. Okay. Now we already figured out the value of Q2 and Q1. So let's just substitute it over here. So the efficiency just comes out to be 1 minus mod Q2, which is NCV T4 minus T1, divided by mod Q1, which was NCV T3 minus T2. Okay, so if you observe here, T4 minus T1 divided by T3 minus T2 is what they asked in option A. So let's try to determine some temperatures here. So the volume at this state, let's just assume the volume is actually V. So the volume at the other state will become 10V, right? Because the compression ratio is given. Now the process from 1 to 2, we know it is adiabatic. So the process follows the equation PV to the power gamma is constant. Now the alternate form of writing this is TV to the power gamma minus 1 is a constant. from here we can say that T1 by T2 equals 10 to the power 1 minus gamma. And 1 minus gamma will be minus 0.5. So this becomes 1 by square root of 10. And from here we get T2, which is the temperature of this state, comes out to be square root of 10 times T1. Okay, so here the temperature is T1 and the temperature over here is square root of 10 times T1. Okay, now let's say the temperature at state 3 is T3. The process for 3 to 4 is also exactly identical, right? So we can just directly say the temperature at 0.4 will be T3 divided by root 10, because we know for a fact that the temperature at state 4 is less than the temperature at state 3. So, and the ratio of these temperatures will be root 10. I just directly wrote it as T3 by root 10. So now if you look at option C, it says that T1 T3 equals T2 T4. So T1 T3 equals T2 T4 would be right because the root 10 cancels out, right? So the cross product is actually correct. So option C would be correct. Okay. So this becomes 1 minus T4. So T4, I am going to write it as T3 divided by root 10 minus the temperature at state 1, which is just T1, divided by, now T2 we figured it out as square root of 10 times T1. So let's just write that over here. Now this simplifies as 1 minus 1 by square root of 10, right? The T3 minus square root of 10 term cancels out from the numerator and denominator. So this just becomes 1 minus 1 by square root of 10. So once you solve this, the efficiency comes out to be around 0.684. So the efficiency is 68% approximately. Now if you look at the option, they are given it as 0.6. So that will be clearly wrong because neta equals 0.6 means the efficiency is 60% and the real answer is 68%. Now if you observe this thing, T4 minus T1 upon T3 minus T2, that is the same as this term over here, right? And that we figured it out, it is 1 by square root of 10. T4 minus T1 divided by T3 minus T2 is 1 by square root of 10. So this, if you calculate, comes out to be 0.316. Rounded off to two significant figures comes out to be 0.32. So, and that matches with option A. So the answer to this question is option A and option C. So now let's move on to the next question. Okay guys, so in this question we have an arrangement that consists of two uniform hemispheres whose radius is 3 centimeters. So it's pretty small, okay, and is made of a material of density 2000 kg per meter cube. The top half is nailed to a support and the space between the two hemispheres is filled with water. The maximum distance between the two hemispheres so that the bottom half doesn't fall is D, and the pressure difference between the top and the bottom hemisphere is delta P. So we'll discuss what they were trying to say with this line a bit later. So we have to figure out D and delta P. So the surface tension is given, acceleration due to gravity is to be taken as 9.8 and the contact angle is to be taken as theta equals 10 degrees. Remember guys, the contact angle was 0 for the combination of water and pure glass. Here is not pure glass, right? It's some arbitrary material. So let's start with the discussion. Okay guys, so this is a situation given to us. So I'm just drawing the flat parts of the hemisphere here. So, and they are given to be separated by a distance of D. And again, the contact angle is given to be 10 degrees, which is basically the angle the tangent to the fluid surface makes with the horizontal plane in this case. So let's try to mark it. So this is the tangent and this is the angle of contact. Now guys, as the shape of the fluid surface is of this sort, it means that the pressure outside is greater than the pressure inside. Only then it can take a shape something like this, right? So as we go from the concave side into the convex side, the pressure should actually decrease. So outside we know the pressure is going to be P naught. Let's say the inside pressure is P. So P is clearly less than P naught. So in order to figure out P, we'll use the Young-Laplace equation, okay? So that basically states that the excess pressure or the pressure difference basically, which in this case is going to be P naught minus P. Right? So this would be equals to the surface tension, let's call it sigma, times 1 by R1 plus 1 by R2, where R1 and R2 are, where R1 and R2 are the principal radii of curvature associated with the surface of the fluid. Okay, so let's try to determine R1 and R2 in this case. So for that, I want you guys to imagine a patch on the surface of this fluid that has a length of, let's say L1. Along this curve, the patch has a length of L1 and it has an length of L2 inside the plane. Okay, so in the plane that you're viewing, it has a length of L1 and into the plane, it has another length of L2. Now, in order to depict the length L2, we are going to draw a top view. So in the top view, so this is basically the hemisphere's flat surface. So this small length is the length L2 that we are talking about. Okay. Now from this we can directly see one of the principal radii of curvatures. Now the small arc of length L2 lies on the circle, right? We know the radii of curvature of the circle is r. So one of the principal radii of curvature is simply the radius of the hemisphere. So now we have to find out the second principal radii of curvature. So for that, what I'm trying to do is I'm going to copy the fluid surface. So guys, again, this is extremely small. Okay, and then I zoomed it a bit. So what I'm doing is I'm taking this fluid surface and drawing it over here. So we want to figure out the radii of curvature of this curve basically. So firstly, we are going to make an assumption that the radii of curvature of each of these small dl lengths is approximately same. Okay, because this is a very small length, right? So we can approximately say that this part is going to be a very small arc of a circle. So let's say the center of that circle is somewhere over here. So if I connect it to the ends, so we are trying to figure out this radii of curvature. Okay, so now if you observe, the contact angle was given to us in the question. So if I draw a tangent at the end, the angle it makes with the horizontal was given to be theta. Now if you observe, the tangent is not perpendicular to the normal. So this whole angle is 90 degrees. So which means this angle is theta as well. So now if I drop a perpendicular, this complete length was given to us as h, right? So half of it is h by 2. So from here we get r2, which is the second principal radii of curvature, as h by 2 secant theta. So finally our expression simplifies as 1 upon h by 2 secant theta. So now the thing is guys, the h is orders of magnitude smaller than r. So separation between the plates is extremely small in comparison to the diameter of the hemisphere. So we usually neglect this term. So now we have one equation relating P and H. So for the second equation, what we're going to do is we're going to balance the forces on the lower hemisphere. Okay guys, so firstly we determine that inside everywhere the pressure is almost P, right? Inside everywhere the pressure is almost constant and it is equal to P. So first we can depict the pressure forces acting on the flat surface of the hemisphere. The magnitude is going to be P times the area of the flat surface, which is pi r squared, right? And then outside everywhere atmospheric pressure of P naught is acting, and as the atmospheric pressure is a uniform pressure, we can use the concept of projected area to write the net atmospheric pressure force, atmospheric pressure P naught times the projected area of this curved surface, which is just pi r square itself. In question number 2, if you guys observe, the pressure difference between the top and the bottom hemisphere. I think what they meant to say was what is the pressure difference between the flat surface and the bottom of the hemisphere. I think that is what they wanted us to figure out. Okay, so the second question, delta P, that they were asking, in my opinion, I think it is equal to P naught minus P. So the other forces are obviously the weight of the hemisphere, W. So W we can easily write, it is the volume of the hemisphere, which is 2 by 3 pi r cubed times the density into G. So we figured out the pressure forces and we wrote down the weight. Now guys, there is one more force acting on the lower hemisphere. That is basically the adhesive force due to the surface tension. So as you can see, the contact angle is 10 degrees. So the surface tension force TDL acting everywhere along the circumferential direction. So let's say this is the flat part of the upper hemisphere. So the surface tension force of TDL is acting everywhere along this circumference, making an angle of 10 degree with the horizontal plane. So if I try to draw it here, so let's say this angle is 10 degrees. Okay, and this is acting along the circumference. So we want the vertical component, so it will be TDL sine 10 degree. So now if you look at this diagram, so the TDL sine 10s are acting in the outward direction as viewed from above. So there is one more force acting along the circumference, and this will be the surface tension T times the total length along which it is acting, which is 2 pi r, and the sine component of it, so this will be sine theta. Okay, and let's call this as F subscript S. Okay, so now once you put in the values, so this actually turns out to be 2.29 10 to the power minus 3 Newton. Now we can say the net upward force equals the net downward force. So the upward force will be P naught minus P times pi r squared plus Fs, and the downward force is actually W, right? So from here, so let's call P naught minus P as delta P. So this will be W minus Fs divided by pi r squared. So once you solve, this value comes out to be 391.19 pascals. You guys may get a different value because I use the calculator here, and in the calculator the value of cos 10 degrees is different to what is provided in the question. In the question it's 0.98. In the calculator I think it is 0.985. So anyways, so this is how we solve the problem at least. So the excess pressure turns out to be around 391.2 pascals. So basically, so the outside pressure is greater than the inside pressure by an amount of 390 something pascals. I think in this option, it's the excess pressure that they're asking about. Again, we got it as 390.19. Again, the value can vary a little bit. Times 10 cubes. So we have to write it as 0.39. So it means I think the value of y should approximately be 0.4. Again, I might have made some mistake somewhere. I am not sure, but the FBD of the problem and the equations are correct, at least. The calculations, you guys check it out once more and comment down below if you're getting the different answer. So again, so now let's try to determine the value of H. So delta P is actually equal to sigma times 1 by R plus 1 by d by 2 secant theta. So, and also in the problem they didn't mention. Now usually we neglect R, so delta P we figured out it is 391.19 and sigma is 0.07. So now as you guys can see, the value sigma by R is actually 7 by 3. So it's extremely small in comparison to the 391 which we have on the left side. So even if we neglect this, it wouldn't change the answer by that much. Okay guys, so once you substitute all the values in, so I used a calculator, so in it the value of cos 10 is a bit different. I don't think it should make that much of a difference in terms of in terms of the first two significant figures. So the answer just comes out to be 0.35 mm. So basically the answer to x is going to be 35 times 10 power minus 2. So the value of x actually comes out to be 35. So now even if you ignore the surface tension term first, it wouldn't make much of a difference. And the reason for that is this term was actually very small. It's 1000 orders smaller than the weight of the weight. So this term is extremely small, and that's the reason why the answer would, even if you guys didn't take that term, you would still get the same answer. And you guys can recheck the calculation once more. So this is the next problem. So we have a small box whose mass is m. It is kept on top of a frictionless ramp with a spring at height h2 from the horizontal table. The ramp is angled at an angle of 30 degrees to the horizontal, and h1 is given to be 4 meters. If the spring is pushed down by an amount of delta x compared to its rest length, so it was initially present at the natural length, and then we pushed it by an amount of delta x, and then it is left, so the box leaves the ramp with some velocity v, and it lands at a distance of delta d meters away. So we have to figure out a delta d and v. So v is quite straightforward, so we'll just use energy conservation here. The compression in the spring is delta x, and the height of the mass from the topmost point is actually, so this angle is 30 degrees. It was compressed by an amount of delta x. So the height is delta x sine 30, which is delta x by 2. Height is going to be delta x by 2. So now we can just conserve energy. So initially when it was in the fully compressed state, the spring potential energy was half k delta x squared. And finally, when it is about top point of the ramp, its spring potential energy becomes 0. The gravitational potential energy is mg delta x by 2, and its kinetic energy is half mv squared. So the final velocity, so the speed comes out to be 1.55 meters per second. Okay. So now the thing is, so now we have to find the value of delta d, and so that is also pretty easy. So this velocity is v. Like equation wise it's easy, it's just a calculation. So this is basically a calculation problem, and the angle with the horizontal is 30 degrees. So if we write down the equation of motion in the y direction, so we can say the displacement in the vertical direction, so the initial velocity vector is in the upward direction, so we'll take the upward direction as positive. So we can say displacement minus 4.5 equals ut, which is going to be v sine 30 into t, minus of half g t squared. And once you solve and take the positive root, the value of time turns out to be 1.0293. And after that it's pretty easy. So the value of delta d is the horizontal velocity, which is v cos 30, times the total time taken t, which comes out to be about 1.382 meters. So the answer to this question should, if I didn't make any calculation mistakes, it'll be 1.55 and 1.38. Okay, so now let's move on to the next problem. Okay guys, so in this question we have a ray of light It enters an arrangement of prisms at a grazing angle. So it just grazes the first prism, which means the angle of incidence is 90 degree. The arrangement contains 5 isosceles right-angled prisms having these refractive indices. If the ray emerges out at a grazing angle of incidence, okay, so even the final emergent ray makes an angle of 90 degree with the prism surface, then which of the relation is satisfied? Okay, so firstly, this angle is 90 degree, right? And let's say the first angle of refraction is, let's say, R1. Okay. So the first thing, guys, that we need to understand is if this angle is R1, then this angle will be 90 minus R1. That is basically its complementary angle. And the reason for that is these two angles are complements of each other. Because it's a right angle prism, if we say this angle is theta, this angle will be 90 minus theta. So which means if this angle is R1, this angle will be 90 minus R1. So now 90 minus R1 is the incidence angle for the second prism. Okay, and let's say this angle is R2. So this angle will be 90 minus R2. And let's say this angle will be 90 minus R3, and you guys get the idea, right? So let's write the Snell's law equation for these two surfaces first. So we can say that sine 90, which is 1, equals mu1 sine R1. So from here we get sine R1 is 1 by mu1. Now similarly we can say mu1 sine 90 minus R1 equals mu2 sine R2. So sine of 90 minus R1 is just cos of R1. So I'm just going to write it like that. So now we can kind of see a pattern, right? So the next term is going to be mu2 cos of R2, and and on the right side it will be mu3 sine R3, and so here it will be mu3 cos R3, and here it will be mu4 sine R4. Okay, and when we reach the final surface, and okay, so now after these four equations, we have finally reached the final surface. So we can say mu5 cos of R4 equals, finally it is going to be 1 sine 90. So it's just going to be 1. So now what we're going to do is we are going to square and add the first two equations. So the left hand side becomes mu1 squared and the right hand side becomes 1 plus mu2 sine R2 squared. So now as you guys can see, in order to get rid of the sine R2, we have to flip equation 3 and then square and add to 2. So then we can get rid of this term. So if we do that, mu3 sine R3 will come on the left side. So after doing that, it will be mu1 square plus LHS would become this, and RHS would become 1 plus mu2 squared. Okay, so now to get rid of the mu3 sine R3, we'll square and add these two equations. Okay, so now we are going to flip this equation and square and add to this to get the next equation. Okay, then finally what we're going to do is we're going to square and add these two equations, and we finally end up with this particular relation. Okay, so yeah, it did require a little bit of work, but the process was pretty straightforward. So this again corresponds to option C. So that was it for this video, guys. If you enjoyed the video, please do like, share and subscribe, and that's it. Thanks for watching.